Well, so we've made it to Chapter 8. So let's take a quick overview of Chapter 8. Chapter 8 deals with friction. And you'll hear it said, friction is fun. I don't know why in the middle of it. So if we take a look at, let me push the button here. We're going to go forward, so hopefully I don't go too far. So friction is essentially just adding another force to our free body diagram. So when we try to push a body, and typically they're blocks or boxes you'll see throughout this chapter, when you try to push a body, right, there's some force that opposes the motion that you're trying to put into the block. So that force that's being applied is simply a friction force, right? The friction force opposes the direction that you're trying to move the body in. So when we deal with a problem with this dry friction, right, the first place we're going to do is, the first step is we're going to draw a free body diagram. Hopefully by this point, right, everything you do, every problem you do, you are drawing a free body diagram. Make sure when you draw your free body diagram that now not only do you include all the external forces that we normally would include, but you now are going to include a friction force. All right, the friction force is always going to be opposite to the way the thing should start to move if it were going to move. Again, remember, we're in statics, so nothing actually moves yet. You're going to determine your unknowns. The one thing you can't assume is, right, we said friction, I said friction is fun, right? Friction, static friction is mu s, a constant, times n, right? Mu s will be given to you in the problem, n is the normal force. You can't assume that is true unless the box or the body that you're trying to move is actually about to move. That's the impending motion condition. If that's given, then friction is fun. If that's not given, then you can't assume that. Then you apply your equations of equilibrium. You apply those equations of equilibrium and you solve for your unknowns, and voila. Right? Not different. We're just adding a new force. Is all we're actually doing. So there's two things that can happen. Right? If I have a box like this, so you see this person is pushing on the box, right? One of two things can happen. Right? That box could slide across the floor, or that box could tip over. Right? So what you are going to be doing is you are going to be figuring out if, and that's basically the whole point of chapter 8, is figuring out, is the item, the box, the body, is it going to slide or is it going to flip over? What they're showing here are two sets of free body diagrams for the box. The one on the left is slipping, right? So think about it, right? You can't see me right at the moment because I don't have the video on, I just have a microphone in front of me. I'm standing here on the floor, right? There is a normal force pushing straight up equal to my weight pushing down, right? If they weren't equal, right? If the normal force was pushing up too harder than my weight was pushing down, I'd fly around the room. That'd be pretty cool, but that doesn't happen, right? If the normal force didn't push up as much as my weight, I would slip through the floor. So you'll notice, right, what do we have in this box? We've got the person pushing, P. We've got the weight of the box at the center of gravity. We have the friction force, F, and we have the normal force coming up. When the normal force is somewhere between the center line and the edge, that implies the box is moving, or it's going to slip, right? That's the impending motion. That's where friction is fun. So that one on the left, right, that friction equals mu n. The one on the right is the box is going to tip. So what's the difference here? Right, you notice that the normal force has moved all the way to the edge. Right, so the normal force is pushing up at the edge. So what's going to happen is when the person pushes on the box, there's going to be a moment and the box is going to tip over on its side. That's the reason why, right, in the first case, the one on the left, the friction is fun. On the second case, that is not true. Friction doesn't equal mu times n in the second case. So, okay, so this here is just kind of giving us the steps for doing this, right? So the top one, as I mentioned to you, is slipping, right? In the slipping case, we know that friction is fun. Friction equals mu Sn. So in that case, we can calculate the friction value and we can solve for the unknowns, right? X is the distance between the normal force and the center line of the box. It's got to be less than half the distance, right? If it's greater than half the distance, then the box is going to tip on the bottom, right? When we have the tipping case, we're going to know the X value, right? Because the normal force is right on the edge. So X is going to be 1/2 of the distance, whatever that happens to be. And we're going to solve in that case for P, N, and F. And we're going to know as a check that F is going to be less than that force, that friction force will be less than mu Sn. So here's an example. So in this particular example, we've got a box. Somebody is pushing, or some force is pushing at point P. You've got the dimensions laid out as shown here. They tell us the weight of the box is 250 pounds. They show us a center of gravity, and they want to know the maximum force P that can be applied without causing movement of the crate, right? Remember, the crate can move one of two ways, right? Number one is that crate can slide along the ground. Number two, that thing can tip over. So we don't know which is going to happen, right? We got to figure that out, and we'll show you how to do that in a second. So what are the steps that you're going to do? We're going to draw a free body diagram of the box. We're going to assume, we'll assume first it's slipping, and then we'll see if our calculations bear out. And if they don't bear out, then we'll check tipping and see if that works. Going to determine your unknowns, make your friction assumptions, apply your equations of equilibrium, and then check your assumptions if necessary, figure out if it works or not. So here is the first case, right? The first case is slipping, right? So you notice that the normal force is some distance x that is between the center line, that center of gravity, and the edge of the box, right? 250 pounds that was given to us in the problem, working through the center of gravity. There's some value P that we don't know what it is. And F we're going to assume is mu N because, in this case, it's going to be slipping. All right, so there's the four unknowns, right? I just mentioned that are P, and F actually isn't an unknown because it's going to be mu N for this case only, and we don't know what X is. So we're going to assume the crate slips. We already said that. And so since that's true, the friction is mu Sn. Mu S was given to us in the problem of 0.4, and we don't know what N is. So let's take and apply our equations. So if we do so, right, if we look at the X direction, what do we have in the X direction? Right, we've got P, and we've got going in the positive X direction, and we've got F going in the negative direction. Right? Remember, F, we're assuming this thing is going to slip, so F is mu N, 0.4 times N. In the Y direction, what do we have? We've got N, and we've got the weight, right? N's going up, the weight's coming down. Right? So from these equations, you can see that, right, N is 258 pounds from the second equation. That's all that's in there. If we plug that into the first equation, we find that the person can push 100 pounds. So we could stop there and say, okay, you can push 100 pounds and the box will get ready to slip in that case. But remember, we don't know if that's true. We made an assumption that that's what the friction value was. So what we can do to prove that is write a moment equation at point 0. You see where that is on the bottom of the box. So what's going to cause a moment around point 0? Well, F and the 250 pounds, right, they both go through 0. So they fall out of the equation. So P we found is 100 pounds. It's 4.5 feet up. And if we put our finger at O and we push at P, the thing's going to go clockwise, so it's a negative value, right? N is going to produce the positive piece. It's going to be 250 pounds, but we don't know how far it is. So we put just an X, or we'll put an X because that's what we put on that's what we got on the paper. So we put an X, we solve for X, and X comes out to 1.8 feet. Whoa, wait a minute, right? The box is 3 feet in length, and 1.5 is half of that. So 1.8 feet means that it's going off the box. So slipping does not happen, right? So if we had stopped and didn't check, we would have got the answer wrong, right? So 100 pounds, somebody pushing 100 pounds, ain't gonna happen. So we're gonna now have to assume tipping occurs. So if tipping occurs, right, remember that normal force moves all the way over to the edge of the box, right? So we can apply our equations again, right? In the x direction, we've got a plus p, we've got a minus f. We can't, in that particular case, right, because we can't assume f equals mu n because we're assuming tipping now. So we just got the p and the f, right? In the y direction, we've got n, and we've got the weight, 250, right? N goes up, positive, 250 comes down. So the normal force is still 250 pounds. And P equals F, right? We get that from equation 1. So if we write a moment equation, again, at point 0, what do we know? Well, we've got P, that's 4.5 feet away, and it's going to produce a clockwise rotation, right? We don't know what P is. All right, the 250 and 1.5 feet, we know both of those in this case, right? That's the normal force pushing up on the edge of the box. With that equation, we can solve for P. When we solve for P, we get an answer of 83.3 pounds, right? So what does that mean? That means if somebody starts pushing on that box, right, once they reach the point that they're pushing at 83.3 pounds, that box is going to tip, right? They would have to push 100 pounds to make the box slip, but obviously, right, if they start to push on the box, they're going to push with 83.3 pounds of force before they get to 100 pounds force, so the box will tip. It will never slide in this particular case. And that is essentially chapter 8.